Now that we've proven this important theorem about what happens when the derivative is bounded less than epsilon, let's make a deduction from this about what happens when the derivative can only be estimated. So our next corollary is going to be a statement about what happens when the derivative is known to have some value approximately equal to m. So, as above, so I mean that f is a differentiable function on an open convex subset of C or R. So if, in fact, f prime of z is somewhere close to m, so it's in the epsilon ball of m, so m is a good approximation to the derivative, then we can also conclude that the difference quotients are also close to m. So in other words, if we have an approximation for the derivative, which is uniformly good over an open convex set, in that the derivative is always pretty close to a certain slope m, then that will also be a uniformly good approximation for the difference quotients of that thing. And the error will be no greater than it was for the derivative. How does this work? We can prove this very easily. We just have to apply the theorem to the function f of z minus mz. So this function has a derivative which is bounded in the appropriate way. So the derivative of this thing has a modulus. That's f prime minus m. Well, I should write f prime of z minus m, and that's bounded less than epsilon. And so the difference quotients for this thing will be bounded less than epsilon. So what does that mean? That means that f of w minus mw minus the quantity f of z minus mz over w minus z is going to be less than epsilon. But we can cancel and simplify, and this is just qwz minus m is less than epsilon, which is this statement that it's in the epsilon ball of m. So this demonstrates that if you have some control over the derivative, even if you don't know that it's close to zero, if you have some control over the derivative, then you can infer that you have equal control over the difference quotient function. And now the next thing that we're going to do is we're going to leverage this to prove that the difference quotient function is a continuous function. Not just continuous in w for fixed values of z and continuous in z for fixed values of w, but a continuous function of two variables. So let's state this as a corollary of that. So this is actually for any open subset now. So let's let x be open, again, in R or in C. And f is, now here I'm going to add a critical hypothesis here. Let f be differentiable with f prime continuous. This is a really essential hypothesis here. Then qwz is continuous on x cross x. So how are we going to prove this? Well, we already know a lot. So let's let delta for diagonal be the set of all xx in x cross x. And then on x cross x minus that diagonal, q of wz is known to be this difference quotient, f of w minus f of z over w minus z, which is a continuous combination. The numerator is just a difference of two continuous functions, and the denominator is a continuous and non-zero function. Why is it non-zero? It's non-zero because if we take away the diagonal, then this thing cannot be zero. So this is a continuous function of two variables, except possibly at the diagonal. Now, what about on the diagonal? Well, let's let z naught be a point on the diagonal. So z naught, of course, is in x. And we know that Q of Z naught is equal to F of Z naught, sorry, F prime of Z naught. And we want to show that for every Z and W both close to Z naught, that we will get Q of WZ very close to this value. So let's let epsilon be greater than 0. And so we're thinking about an epsilon neighborhood of this target value, F prime of Z naught. Now, F prime is continuous. So by the continuity of F prime, so there is a delta greater than 0, so that on the ball of radius delta of the point Z naught, so F prime of Z naught, F prime of Z is always going to give us a value which is in the epsilon neighborhood of F prime of Z naught. So this is a direct application of the continuity of F prime. Basically, there's a delta ball of Z naught where F prime takes all of its values into this epsilon ball of F prime of Z naught. That's the continuity of F prime. Now, this ball, so this ball here around Z naught of radius delta is not only open, but it's also convex. And that means that this theorem and its corollary apply. And so here we have a slope, and we have a uniform estimate that applies on this open convex set. F prime of Z is always within epsilon of this value. And so what we can deduce then is that Q of WZ is always going to be in that range under the same conditions. So then for all W and Z in that very same ball, then we get Q of WZ is also going to be in that ball of radius epsilon around F prime of Z. I noticed here there are typos here. There's a typo that should not be a modulus there. It wasn't a modulus there. So, so that demonstrates that we have the desired condition, right, for every W and Z in this ball. So that is, let me rephrase this a little bit. For every pair WZ in this ball around Z naught of radius delta crossed with itself, then we have Q of WZ is in that ball centered at F prime of Z naught radius epsilon. So the reason I'm rephrasing it this way is to showcase that this is an open neighborhood of the point Z naught on which we get the values of Q into this target ball here. And that shows that Q is continuous. So therefore Q is continuous at the point Z naught on the diagonal, which is what we were trying to show. We already have it continuous off the diagonal. Now it's continuous on the diagonal. And so that gives us that we have Q is actually a continuous function of two variables.